Welcome to the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our first lecture covering material from Chapter 7. We begin Chapter 7 with some rules that describe the order in which orbitals are filled for multi-electron species. We've previously seen that the lower energy orbitals will fill first and that each orbital can hold 2 electrons. However, Hund's rule provides additional information regarding the orbital filling when we have multiple orbitals at the same energy, like the 2p subshell where there are 3 orbitals. In this image, we've represented the orbital with a line. The 1s orbital is of the lowest energy and will be filled first, followed by the n equals 2 orbitals. Notice how there are 3 lines, or orbitals, associated with the 2p subshell and 5 for the 3d subshell. Also notice that we have included the quantum number L at the top of the diagram. L equals 0 are s orbitals, and these are spherical in shape. The hand-drawn curved lines represent a piece of the Bohr diagram where each circle around the nucleus represents an orbital. In the case of a single-electron atom, the sp and d subshells are all of equal energy if they have the same n value. This is only true for the hydrogen atom, which only has 1 electron. This diagram shows the energy levels for a multi-electron atom. The reason that the orbitals with equal n values are not of equal energy is due to a shielding effect. What is meant by this is that the nucleus is shielded by electrons which exert repulsive forces on the electrons that are further from the nucleus. The further from the nucleus, the more shielding experienced, and this results in overlap of energies, as we see with the 4s and 3d orbitals. The energy for a subshell in a multi-electron species is related to the sum of the n and l quantum numbers, as opposed to just the n value alone. This slide provides a brief summary of orbital energy for multi-electron species. We stated earlier that electrons will fill the lowest energy orbitals first, and using n plus L to determine the energy results in a fill order as noted at the bottom of the slide. There are a couple of methods that are commonly used to memorize this fill order. Personally, I like to use my periodic table to determine fill order. I simply read the table like a book. What I mean is that I start at the upper left and read to the right. When I get to the end of the line, I go back to the left and start on the next line down. If you remember your SP, D, and F blocks, this is quite simple. 1s followed by 2s, then 2p. Next is 3s, 3p, 4s, 3d, then 4p. Another method for fill order is to set up a graphical method using the n values and l values. You can see here how the diagonal lines will match the fill order. This method is fine, but I prefer the periodic table. Use what works best for you, because this is going to be very important. In order to write an electron configuration, we need to know the fill order of the subshells, and we also need to realize how many electrons can exist in each subshell. The s orbitals will only have 2 electrons, while the p orbitals can hold 6, d can hold 10, and f can hold 14. These come from the m sub l values that determine how many orientations of the orbitals exist. In red, we have illustrated the electron configuration for fluorine. Fluorine has 9 electrons, and they will fill in order as mentioned. Uranium is near the top in green, and this is very cumbersome. Fortunately, there's another method for writing electron configurations that we will cover next. Before we introduce the shortcut for large atoms, we should mention the orbital box notation. This notation uses lines or boxes to represent the orbitals. Notice the spacing between the orbitals. This is required, so make sure that your boxes for subshells are spaced from other subshells. In this method, each electron is represented by an arrow. The up or down direction represents our m sub s, or our spin. Another mention is that even if there are some orbitals empty for a given subshell, you have to draw them and leave them empty. For aluminum, there is 1 electron in the 3p orbital, but all of the 3p orbitals are shown. The noble gas notation makes writing electron configurations easier. The method is to write the previous noble gas in brackets to represent that number of electrons, then proceed as you would after the noble gas. The example given is for the silicon atom, and we can represent the first 10 electrons with the noble gas neon in brackets, and then write the remaining electrons. The remaining electrons are referred to as valence electrons. These are the outermost electrons, and they will be involved in bonding, and we'll see this in the next chapter. There are some exceptions to our fill order. We will hold you accountable for 5 that are listed here. For these elements, an electron from the s orbital is promoted to the d orbital to make all 5 either half-filled or a completely full d. For now, we will just say that this is a more stable configuration and it is preferred. The 4s and 3d orbitals are very close in energy, and that allows this to occur. Practice these and be prepared for this on your exam because exceptions make great test questions. We can also write electron configurations for ions, but first let's review ions. Ions are charged atoms, and they can be either negatively charged or positively charged. A neutral atom has the same number of electrons and protons. If a neutral atom gains an electron, it becomes a negative ion, or an anion. Likewise, losing electrons results in a positively charged cation. Anions are more simple. For an anion, we simply add the extra electrons following the fill order. For example, a fluoride ion will have a full 2p subshell, which is the same configuration as the noble gas neon. You will quickly realize that many ions have the same configuration as the nearest noble gas. Cations are slightly more complicated. Since we have to remove electrons, we have to know which subshell is going to give up these electrons. For magnesium, we will take the 2 electrons from the highest n, or the 3s orbital. Notice how the magnesium ion has the same electron configuration as the noble gas neon. What about tin? Tin has s and p orbitals occupied. In this case, we start with the highest L value, so we will remove electrons from the 5p orbital first. It is helpful with cations to write the electron configuration of the neutral atom first, then rearrange the configuration to n order as opposed to fill order. You can see in this example where the 4d came before both of the n equals 5 orbitals. Recall the transition metals are sometimes polyvalent, meaning they can form more than one ion. With some practice, you will see why the 2+ ion is so common amongst the transition metals. And note on exceptions. Don't promote electrons after forming ions. If the neutral atom is one of the exceptions, then you write the configuration with the promotion, then you adjust to form the ion. Chromium is one of the exceptions. The neutral atom has 1 electron in the 4s orbital and 1 electron in each of the 3d orbitals. We remove the 4s electron first, followed by 2 of the 3d electrons to get the 3+ ion. We complete this lecture with an example of the anion in both SPDF notation and orbital box notation. This lecture covered a lot of material. Before the next lecture, you will want to be able to write electron configurations using 4 methods: full SPDF, full orbital box, and the noble gas notation for each. You will also need to be able to recognize the exceptions and write the configurations for them. Lastly, you will need to be able to write electron configurations for both cations and anions. This may seem overwhelming at first, but you can master this with practice. Thanks for watching. Please give the video a thumbs up and subscribe if you'd like to see more mini lectures on the Professor's DuBois channel.